Imagine standing in the middle of a vast gray desert where the ground crunches like powdered glass beneath your boots, where the sky above is pitch black, sprinkled with unmoving stars, and the earth rises on the horizon like a shimmering blue gem. Now imagine building a home here, not a shelter, not a tent, but a fully operational base where people can live, work, and thrive. This isn't science fiction anymore. This is the future of humanity's off-world journey, and the moon is our first stop. But how do you build in a place that has no atmosphere, no water on the surface, and temperature swings that could fry or freeze steel within hours? The challenges of constructing a lunar base are staggering, yet the ingenuity of scientists and engineers is rising to meet the moment with ideas that border on science fiction, yet are grounded in physics, chemistry, and logistics. The first hurdle is the environment itself. The moon is a land of extremes. Daytime temperatures soar to 260 degrees Fahrenheit, while nights can plunge to -280. That alone would destroy most Earth-based construction materials, warping metal, cracking concrete, or rendering electronics useless. Add to that the constant bombardment of radiation from the sun and cosmic rays, which can penetrate deeply into materials and human tissue, and you're faced with a deadly gauntlet. Then there's the ever-present threat of micrometeoroids, tiny high-velocity projectiles capable of punching holes through metal like bullets. And let's not forget lunar dust. Fine as flour, sharp as glass, and electrostatically charged, it clings to everything and wears down joints, seals, and even the lungs if inhaled. Building on the moon means surviving all of that, day after day, indefinitely. So how do we do it? The answer starts with a powerful concept known as in situ resource utilization, or ISRU. The idea is simple: use what's already there instead of hauling everything from Earth. And the most abundant material on the moon? Regolith. This dusty, rocky soil is a nuisance for astronauts, but a goldmine for builders. Scientists have been experimenting with turning regolith into concrete-like materials. By applying heat through solar furnaces or microwaves, lunar dust can be sintered, fused into solid blocks, or even extruded into slabs and columns. Some projects even envision mobile 3D printers, robotic rovers that roll across the surface, printing walls, domes, and support structures layer by layer from the very soil beneath their treads. But regolith isn't the only building block. At the moon's poles, especially in craters that never see sunlight, water ice is buried beneath the surface. That ice can be harvested not just for drinking water or oxygen, but potentially for use in construction. Ice, especially when combined with other materials, can act as an effective radiation shield. Imagine transparent ice domes with walls several feet thick, allowing filtered light in while keeping radiation out. Inflatable habitats wrapped in ice-based shells could become both functional and protective homes. Then there's the role of robotics. Humans won't be laying bricks or welding beams in bulky spacesuits. Instead, autonomous robots, guided by artificial intelligence and equipped with specialized tools, will perform most of the construction. These machines can work non-stop in harsh conditions, self-correct, and adapt to their surroundings. Swarms of small bots might handle tasks like welding seams, moving materials, or laying down solar panels, while larger multi-limbed robots handle structural assembly. NASA and other space agencies are already developing these systems with remarkable capabilities. The architectural designs themselves are changing too. Instead of traditional buildings, early bases may look like expandable pods or interconnected tunnels. Inflatable habitats, packed into small volumes for launch, can be expanded on the lunar surface to create livable interiors. These can then be covered with layers of regolith using robotic bulldozers to insulate against temperature swings and radiation. Over time, more permanent structures can be built: thick-walled bunkers, regolith brick habitats, or even subterranean dwellings carved into lava tubes that lie beneath the moon's surface. These natural caves offer stable temperatures and protection from radiation, making them ideal sites for long-term habitation. And what about energy? With no fossil fuels and no grid, power must come from the sun. But remember, lunar night lasts about 14 Earth days. Solar arrays must be designed to store enough energy to last through this dark stretch. Alternatively, bases near the poles might enjoy near-constant sunlight and are prime locations for solar farms. Advanced battery systems or even small modular nuclear reactors could supply consistent, long-term energy, essential for life support, heating, communication, and construction. Every system must be closed-loop, sustainable, and efficient. Wastewater must be purified and reused. Air must be continuously scrubbed and recycled. Food may need to be grown hydroponically or in sealed biomes. Each of these challenges is being studied and tested in analog environments on Earth. from simulated lunar missions in the deserts of Arizona to underground bunkers in Iceland. The key is redundancy, reliability, and resilience. The moon isn't just a rock in space. It's a stepping stone. Establishing a base there isn't about bragging rights. It's about building the infrastructure and experience needed to go further. Mars, the asteroid belt, maybe even Europa or Titan someday. A lunar base can serve as a launch pad for deep space missions, a laboratory for studying how life adapts to space, a mining outpost for rare elements, or a tourist destination for the ultra-rich. It could become a symbol of unity and ambition for all of humanity. Yet none of this will happen without vision, funding, and international collaboration. NASA's Artemis program aims to land humans back on the moon this decade, and they're partnering with private companies like SpaceX and Blue Origin to develop the next generation of landers and habitats. China, too, has set its sights on lunar exploration with a roadmap that includes crewed missions and base construction by the 2030s. The European Space Agency, Russia, India, all are players in this new space race. But this race isn't about beating rivals. It's about survival, about innovation, about securing a future where Earth is not our only home. And while it may seem distant, the impact of these missions will reach every corner of our lives. Technologies developed for the moon will lead to advances in energy, materials, medicine, and AI. Young people inspired by these missions will become the next generation of engineers, scientists, and explorers. The moon base is more than a goal. It's a proving ground for the soul of humanity, our drive to explore, adapt, and overcome. And as the first bricks are laid in lunar dust, a new chapter in human history begins. If this vision of the future inspired you, if you believe humanity's next giant leap is within reach, then join us in following these developments. Subscribe to the channel, like this video, and share it with anyone who still thinks the moon is just a dead rock. The truth is far more exciting. The moon is becoming our new frontier, and the future is already under construction. The first footprints on the moon were a statement of intent. But now the intention is permanence. As we move deeper into this century, the moon is no longer just a destination. It's becoming a construction site. But what does that really mean? What does it take to build not just for a visit, but for a lifetime in an environment so alien it seems almost hostile to human life? The vision is bold. Structures that rise from lunar dust, powered by sunlight, insulated from radiation, and supported by autonomous machines humming across the regolith. But for that to happen, we must invent the rules of extraterrestrial construction from scratch. The first step forward lies in redefining what building materials mean in space. Instead of shipping bricks and beams from Earth, engineers are now looking at the moon itself as the source of what we need. Lunar regolith, once considered a nuisance, is now being treated as a gift. Its fine, powdery grains, though abrasive and electrostatically charged, can be transformed into building materials using sintering, a process of heating particles until they fuse. With this, we're not just dreaming of 3D printing lunar habitats. We're developing entire robotic systems capable of autonomously converting moon dust into load-bearing walls, domes, and even landing pads. This concept, known as In Situ Resource Utilization or ISRU, is what separates science fiction from near-future reality. It reduces dependence on Earth and significantly cuts down mission costs. But it comes with new engineering puzzles. For example, how do you ensure structural integrity without rebar, or prevent cracks when temperature swings range from -280 degrees Fahrenheit at night to over 260 degrees during the day? New types of cement and regolith-based composites are being designed to expand and contract with minimal stress fractures, and these materials are already undergoing tests in lunar simulant labs on Earth. However, it's not just about walls and roofs. A lunar habitat must be a life support machine. Every inch of the structure must contribute to sustainability. That's where smart materials enter the picture. Substances embedded with sensors or self-healing capabilities that can detect damage from micrometeoroids or temperature extremes and react in real time. Some of these materials may be able to adjust opacity depending on solar exposure, store heat during the day, and release it at night, effectively acting as passive thermal regulators. Water is another critical component. While carrying large volumes from Earth is infeasible, frozen water has been detected in the permanently shadowed craters near the lunar poles. Future habitats may not only mine this ice for drinking and life support but also use it as a construction material. Ice walls could provide excellent radiation shielding. In fact, ice combined with regolith in layered domes may become a hallmark of lunar architecture, beautiful, strange, and functional. We also need to consider energy. Solar power will dominate lunar energy strategies, especially in regions like the peaks of eternal light near the South Pole, which receive almost constant sunlight. Large solar arrays, possibly printed directly onto the lunar surface using conductive inks and robotic applicators, will harvest this energy. But nighttime lasts nearly 14 Earth days on the Moon, requiring a combination of battery storage, hydrogen fuel cells, and possibly even small nuclear reactors to keep habitats running. Automation will play a defining role. Construction robots equipped with advanced AI will act as lunar laborers, laying foundations, printing structures, welding joints, and inspecting infrastructure, all while being monitored by human supervisors back on Earth or in lunar orbit. These robots must be rugged, adaptable, and capable of navigating the regolith, which behaves more like quicksand in some areas than firm ground. NASA and ESA are already testing multi-legged and wheeled rovers that can handle such unpredictable terrain. Inside these habitats, life must be as Earth-like as possible to maintain physical and psychological health. Closed-loop systems will recycle air, water, and even waste. Hydroponic farms will grow leafy greens under artificial light, and future bioreactors may produce protein from algae or fungi. The interiors will need to be shielded not just from radiation but from isolation. Designers are working with psychologists to create environments that feel natural, with curves, soft lighting, and even virtual windows that simulate Earth skies and landscapes. Social and emotional health will be vital. Loneliness, stress, and sleep disorders are known risks in space. Incorporating Earth-like cycles, such as 24-hour lighting changes, can help, as can communication delays being minimized via relay satellites to preserve the illusion of real-time conversations with loved ones on Earth. Virtual reality, social games, creative outlets, and mental health check-ins will become part of daily life, as essential as any physical maintenance. But why invest all this effort in a place so far from home? The answer lies in legacy and leverage. A permanent lunar base is a stepping stone to Mars and beyond. It allows humanity to test technologies and techniques in a relatively nearby, but still hostile environment. It's a laboratory for biology, geology, and even industry. Mining rare elements from the Moon, manufacturing parts in microgravity, and launching missions from its low-gravity well could redefine our economy. Tourists may visit lunar hotels, scientists could live there seasonally, and companies might begin building infrastructure that leads to off-world commerce. There's also the potential for unexpected discoveries. Just as Antarctica yielded microbial life that transformed our understanding of biology, the Moon may hold secrets buried in its ancient crust. Trapped gases, ice chemistry, and strange mineral formations could teach us more about the solar system's formation, and about ourselves. To reach that future, international cooperation will be essential. The Artemis Accords, signed by numerous nations, set the groundwork for peaceful exploration and shared development. Countries are bringing unique strengths: Japanese robots, European habitats, Canadian robotic arms, and American propulsion systems. Private companies like SpaceX, Blue Origin, and Espace are reshaping launch economics and enabling lunar cargo to become a reality. We stand on the brink of a new architectural revolution, one not defined by cities of glass and steel, but of regolith and radiation shielding. The first permanent moon base might not be a towering structure, but a series of interconnected domes nestled near the lunar south pole, glowing faintly under the sun's eternal glare. But within those domes, humanity will be writing a new chapter. This isn't just about survival, it's about thriving. It's about daring to imagine that the moon can be more than a rock in the sky. It can be home. A place where children might one day play in gravity 1/6 of Earth's, where science is born from silence, and where the impossible becomes routine. It will be hard. There will be setbacks, maybe even tragedy. But the drive to explore, to build, to endure, that's who we are. So as we look up at the moon tonight, know that plans are unfolding. Not in silence, but in sparks of welding robots, in data streams from rovers, in blueprints sent across time zones and languages. The moon is waiting, not for another flag, but for a foundation. And we are coming. If this vision of the future excites you, if you believe in the incredible journey ahead, support the mission. Like this video, share it with others who dream big, and subscribe for more explorations into science, space, and the bold steps we're taking beyond our world. The moon is calling, and together we'll answer.